Hey friends, welcome to the YouTube channel All About Electronics. In the previous introductory video, we understood what is ADC and DAC. And then we had listed the different types of ADC and DAC which are commonly used in electronics. So in this video, let us understand in detail about the binary weighted resistor type of DAC. But before we do that, let us briefly discuss about the DAC, as in the previous video we have mostly discussed about the ADC. So this DAC converts the digital input into the analog output. So here the digital bits are applied as an input, and at the output, according to the applied digital bits, we will get the analog output. And apart from this input and output, the reference voltage is also applied to this DAC. So in some DAC, this reference voltage is generated internally, while in some DAC it is applied externally. So this reference voltage decides what is the maximum output voltage which is possible for the given DAC. Now here, for the particular digital code, we will get the fixed analog output. But if the digital code is changing continuously at the fixed interval, then the output will also change continuously. But actually if you see the output of the DAC, then it will look like this. And by passing the output through the filter, it is possible to smooth out the output. But here, actually the resolution of the DAC decides how closely the output of the DAC matches with the actual waveform. And by increasing the resolution, this step size can be reduced, and then the output of the DAC will be much closer to the actual waveform. Now, as I said in the previous video, the resolution of the ADC or DAC is defined in the number of bits. So for a 3-bit DAC with a 5 volt of reference voltage, the resolution can be defined as V reference divided by 2 to the power n. Now many times this reference voltage is multiplied by the internal gain of the DAC. So there is always a multiplying factor with this reference voltage, and it depends on the construction of the DAC. That means how the DAC is actually designed. And sometimes the manufacturers also provides the provision to the user to select the internal gain from the specified values. But here let us assume that the value of K is equal to 1. So the reference voltage can be given as 5 volt divided by 2 to the power 3, that is equal to 0.625 volt. So here is the transfer function of a 3-bit DAC with a 5 volt of reference voltage. And again here we are assuming that the internal gain or the value of K is equal to 1. So here if we change the code by 1 LSB, then the output will change by a 0.625 volt or by a 5 by 8 volt. So we can say that the voltage which is required for the 1 LSB change is equal to 0.625 volt. Also if you see the step size or the change in the voltage between the two codes, then it is equal to 5 by 8 volt. So from this we can say that the step size for the given DAC is equal to 0.625 volt. So whenever we go from the code 000 towards the 111, then the output will change in the step of 5 by 8 volt. And the maximum output which we will get corresponds to 111 is equal to 35 by 8 volt. So this maximum output voltage which we can get from the DAC is known as the full scale output voltage. So we can say that for this 3-bit DAC with a 5 volt of voltage reference, the full scale output voltage is equal to 35 by 8 volt. Or we can write it as 7 by 8 volt multiplied by reference voltage, because over here this reference voltage is equal to 5 volt. Now here once again we are assuming that the value of internal gain or the value of K is equal to 1. So if the value of K is not 1, in that case this factor will also get multiplied by the factor of K. So we can write this expression as 2 to the power 3 minus 1 times V reference divided by 2 to the power 3. Or in general we can write it as 2 to the power n minus 1 times V reference divided by 2 to the power n, where here n is the number of bits of the DAC and V reference is the reference voltage. And once again here we are assuming that the value of K is equal to 1. Now if you notice over here, this V reference divided by 2 to the power n is nothing but the step size of the DAC. So from this we can say that the full scale output voltage is equal to 2 to the power n minus 1 times step size. Or from this we can say that the step size or the resolution of the DAC is equal to full scale output voltage divided by 2 to the power n minus 1. So from this we can say that the resolution or the step size or the voltage corresponds to 1 LSB is equal to V reference divided by 2 to the power n, that is equal to full scale output voltage divided by 2 to the power n minus 1. And if there is any kind of internal gain, then this V reference will get multiplied by the factor of K. And we can also write this full scale output voltage as V reference minus 1 LSB. So I hope these terminologies regarding the DAC are clear to you. Alright, so now let's talk about the binary weighted resistor type of DAC. So this DAC can be designed by using the op-amp as a summing amplifier. And we have already discussed in the earlier video of the op-amp that how the summing amplifier can be designed using the op-amp. So for more information you can check that video. So this circuit which is shown over here is the inverting summing amplifier. And the output voltage of this amplifier can be given as V output, that is equal to minus RF divided by R1 times V1 plus RF divided by R2 times V2 plus RF divided by R3 times V3. And here this negative sign indicates that the output voltage will be 180 degree out of phase with the input voltage. So here if we assume that all the resistors are equal and let's say the value of all resistor is equal to R, in that case the output voltage Vout can be given as minus V1 plus V2 plus V3. And in the same circuit, if we assume that this R2 is equal to 2R and R3 is equal to 3R, in that case the output voltage Vout can be given as minus V1 plus V2 divided by 2 plus V3 divided by 3. So in this way, by changing the resistor value, we can scale the individual inputs. So in this summing amplifier, if the inputs and the weightage of each resistor is according to the binary number, then it can be used to convert the digital input bits into the analog output. So as you can see over here, the weightage of each resistor is in the multiple of 2. And according to the binary number, the resistors are connected to either a reference voltage or to the ground terminal. For example, for the binary code of 101, the LSB B0 and the MSB B2 are connected to the reference voltage, while this digit B2 is connected to the ground terminal. And these resistors can be connected to either reference voltage or ground via these switches. And it is possible to control these switches either using the microcontroller or the microprocessor. So over here, in general, the output voltage Vout can be given as minus RF times V reference multiplied by V2 divided by R plus B1 divided by 2R plus B0 divided by 4R. And over here, if you observe, B2 is equal to 1, B1 is equal to 0 and B0 is equal to 1. So if you put the values of this B1, B2 and B0, then we can write the output voltage Vout as minus RF times V reference divided by R multiplied by 1 plus 0 plus 1 by 4. Now here, if we assume RF is equal to R and the value of V reference is equal to 5 volt, in that case, the output voltage Vout will be equal to minus 5 times 5 by 4, that is equal to minus 25 by 4 volt. Now if you see the earlier transfer function for the 3-bit DAC, then for the code of 101 we were getting an output voltage of minus 25 by 8 volt. That means here the output voltage is double, or we can say that here the internal gain of the DAC is equal to 2. That means for this type of DAC, whenever RF is equal to R, at that time the reference voltage will get multiplied by the factor of 2. And that is why the output is minus 25 by 4 volt instead of 25 by 8 volt. So here, if RF is equal to R by 2, in that case, we would have got an output voltage of 25 by 8 volt for the code of 101. So for the given DAC, the proportionality factor or the internal gain of the DAC depends on how the values of resistors are chosen. So in general, for this binary weighted resistor type of DAC, the output voltage can be given by this expression, where here N represents the number of bits of the DAC. So for the given circuit, let's say if RF is equal to R and V reference is equal to 5 volt, then for the code of 111, the output voltage Vout can be given as minus 5 times R divided by R times B0 divided by 4 plus B1 divided by 2 to the power 1 plus B2 divided by 2 to the power 0. And here, as all the bits are 1, so this B0, B1 and B2 will be 1. So the output voltage Vout will be equal to minus 5 times 1 by 4 plus 1 by 2 plus 1. That is equal to minus 35 by 4 volt. And if you notice, this output voltage is also a full scale output voltage of the given DAC. So for this configuration, we can say that the full scale output voltage is equal to minus 35 by 4 volt. Now if you compare this full scale output voltage with the earlier 3-bit transfer function, then it is double. That means we can say that over here the internal gain of the DAC is equal to 2. That means the reference voltage will get multiplied by the factor of 2. And over here, if you see the resolution or the voltage corresponds to 1 LSB, then it will be equal to full scale output voltage divided by 2 to the power n minus 1. So here the full scale output voltage is equal to minus 35 by 4 volt and the value of n over here is equal to 3. That means 2 to the power 3 minus 1. So the value of 1 LSB will be equal to minus 35 by 4 times 7. That is equal to minus 5 by 4 volt. So in this way, for the given DAC, if we know the value of full scale output voltage and the number of bits, then we can find the resolution. Now here, if we assume that I1, I2 and I3 are the currents which are flowing through all these resistors, then the total current IT will be equal to the summation of all these currents. That is equal to I1 plus I2 plus I3. Or we can say that is equal to V reference divided by R multiplied by B2 divided by 1 plus B1 divided by 2 to the power 1 plus B0 divided by 2 to the power 2. Or in general, the total current I can be expressed by this expression. So in this circuit, if R is equal to 1 kilo ohm and the reference voltage is equal to 5 volt, then for the binary code of 111, the total current IT can be given as 5 divided by 1 kilo ohm multiplied by B0 divided by 2 to the power 2 plus B1 divided by 2 to the power 1 plus B2 divided by 2 to the power 0. And here, as all the bits are 1, so we can say that the total current IT will be equal to 5 milliampere times 1 by 4 plus 1 by 2 plus 1. That is equal to 35 by 4 milliampere. So in this way, we can also calculate the maximum current which is flowing through the DAC. Or for the given DAC, with a particular value of maximum current, we can also decide the value of R accordingly. So that is being said, here is the example of a 6-bit binary weighted resistor type of DAC. And as you can see, the value of R is increasing in the multiplication of 2. Or we can say that it is increasing in the proportion of 2 to the power of n minus 1 minus I, where I is the position of the bit starting from 0 to n minus 1. So as you can see, as the number of bits increases, the ratio between the highest and the lowest value of the resistor will also increase. So for a 10-bit DAC, if the value of R is equal to 1 kilo ohm, then the maximum value of the required resistor will be equal to 2 to the power n minus 1 times R. So for a 10-bit DAC, it will be equal to 512 kilo ohm. On the other hand, if we talk about the 12-bit DAC, then considering R is equal to 1 kilo ohm, the maximum value of the required resistor would be around 2 mega ohm. So as the number of bits increases, it is very difficult to produce all these resistors in the same proportion, that means in the same multiplication factor of 2 with a good accuracy. For example, even if we consider that all the resistors have a 1% tolerance, then also it can produce a significant error in the output. So let's take one example to understand that. So here, let's say all the resistors have a 1% tolerance, and here we are also assuming that the RF is equal to R, and we have been asked to find the maximum and the minimum value of the output voltage for this code. And here also assume that the reference voltage is equal to 5 volt. So first of all, if we assume all the resistors are ideal, in that case the output voltage Vout can be given as minus 5 times R divided by R times B0 divided by 32 plus B1 divided by 16 plus B2 divided by 8 plus B3 divided by 4 plus B4 divided by 2 plus B5. And here, as all the bits are 1, so we can write this output voltage Vout as minus 5 times 1 by 32 plus 1 by 16 plus 1 by 8 plus 1 by 4 plus 1 by 2 plus 1. And if we simplify it, then the output voltage Vout will be equal to minus 5 times 63 divided by 32. That is equal to minus 9.84375 volt. And this will also be a full scale output voltage considering all the resistors are ideal. And from this we can say that the voltage corresponds to 1 LSB, or the resolution of the DAC will be equal to full scale output voltage divided by 2 to the power n minus 1. That is equal to minus 9.84375 divided by 63. And if you calculate, then the value corresponds to 1 LSB will be equal to minus 0.15625 volt. So this will be the value of 1 LSB when we assume that all the resistors are ideal. Now if we assume 1% tolerance in the resistors, then the output will be maximum whenever this RF is maximum and R is minimum. That means we can say that whenever RF max is equal to 1.01 times R and R minimum is equal to 0.99 times R. So the maximum output voltage Vmax will be equal to minus 5 times 1.01 times R divided by 0.99 times R and multiplied by summation of all these bits. And as we have calculated previously, it will come out as 63 by 32. So if we simplify it, then the maximum value of the output voltage will be equal to minus 10.0426 volt. And similarly, to find the minimum value, the RF will be equal to 0.99 times R and R will be equal to 1.01 times R. So the minimum value of the output voltage will be equal to minus 5 times 0.99 times R divided by 1.01 times R and multiplied by this factor, which is equal to 63 divided by 32. So further if you simplify it, then the minimum value which we will get will be equal to minus 9.6488 volt. So this will be the minimum value which we will get if we assume that the tolerance in the resistor is equal to 1%. Now if you compare this voltage with this ideal voltage, then the difference between the two is equal to 0.1949. That means we can say that the difference between the ideal output voltage and the minimum output voltage is equal to 0.1949 volt, which is in fact more than 1 LSB, because as we have calculated earlier, the value of 1 LSB is equal to 0.1562 volt. That means if we use the resistors with a 1% tolerance, then the maximum error in the output will be more than 1 LSB. So to avoid that, the tolerance of all resistors should be less than 1%. And it is hard to achieve as the number of resistors in the circuit will increase. And that is why this type of DAC is not used whenever the high accuracy and the high resolution is required. And for that, this second type of DAC is oftenly used, which is known as R2R ladder type of DAC. So we will discuss more about it in the next video. So I hope in this video you understood how we can design a binary weighted resistor type of DAC. So if you have any question or suggestions, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to this channel for more such videos.